Alright, so what we'll do is we'll talk about this example that we left off. Is usually when I get stuck on a problem in class, I make a video out of it. I haven't made a video, but I will make a video of this. But I got the solutions down here at least. And what we have here is this differential equation. And one of the things that make things a little bit easier for us with this, with the non-homogeneous differential equation is the superposition principle. And the superposition principle allows us to take this right-hand side, and the right-hand side contains a couple of different terms. What we could do with those terms is that we can break them up to two different problems so that the two problems that we're dealing with are, or the two problems that we're dealing with have a right-hand side that's easier for us to manage one at a time. So what we could do is we can find a solution for the non-homogeneous term, or the non-homogeneous differential equation, that has one, or in this case two, of the terms, and then a different non-homogeneous differential equation that has the other term. By doing that, we're allowing ourselves to find particular solutions for those non-homogeneous differential equations, and the superposition principle allows us to take those two particular solutions and just add them up. And so that's what's going to happen. So initially, our guess would look like this. The first one is a linear term, and so here they call it y sub p sub 1. And so that's a linear term. And then the second one is an exponential function. That's e to the negative 2x. Unfortunately, our linear term kind of matches with this 1. And so when that happens, what we want to do is we want to multiply your guess by an extra x. The way this works is that if one of your fundamental solutions matches the guess that you have, or one of your fundamental solutions is linearly dependent with one of the guesses that you have, what you need to do is you need to multiply it by x. Okay, so by multiplying this by x, our y sub p sub 2, or our y sub p sub 1, will be ax squared plus bx. And so given this new guess for your solutions, for your particular solution, we find the first and second derivatives, we put it back into the differential equation, the non-homogeneous differential equation that only contains that linear right-hand side, and then we are able to solve for a and b. Okay. Last time when we tried doing this, we weren't able to solve for those undetermined coefficients because our guess matched, or was linearly dependent with one of the fundamental solutions. Yeah. That's fine. I think if you kept that y sub p, that it has the linear term plus the exponential term, it would just get a little messier. But it should result in the same, or close to the same, minus some constants. Yeah. Yes. So if you have two different exponentials, like e to the negative 2x and e to the positive 4x or something, yeah, you can split it up the same way, which might be a homework problem. So that's the first one. The second one, y sub p sub 2, is the exponential problem. And so again, we take the first and second derivatives, but now because there's an extra x in there, you have to be careful with the product rule. And as I was doing this, working on this after class, I was, there's getting some little mistakes with the product rule. So make sure when you do the product rule, you do it correctly. So with the product rule, especially the second derivative, because your first derivative has a product rule, and your second derivative, well, there's now one product rule and one regular term that you can try to combine. But the idea is to simplify it and then put it together in your original non-homogeneous differential equation, and that will allow you to find your undetermined coefficient. So we got C is equal to 1/2. And so now you have the fundamental solution from your homogeneous differential equation, and here's your A is equal to 1/2, and your B is equal to 2. So this is from the first non-homogeneous solution, particular solution. And then the last one is a 1/2. C is equal to 1/2. And then you tack it on to the x times e to the negative 2x, and then that's your final solution. I put this differential equation into Wolfram Alpha and had it solved, and then they came up with extra constants. And so after looking at it carefully and like combining all the constants, it turns out to be the same as this. So this is a pretty good solution, and I think this solution is cleaner than the one that I got from Wolfram Alpha, because Wolfram Alpha included a bunch of other constants there that would have been combined with C1 and C2 here. And so clearly they did a different algorithm from this, but I think this gets the most bare bones, cleanest sort of solution for your differential equation in terms of the functions and the fundamental solutions and the linear independence of the functions. All right. So you can take a look at that, and if you submitted a solution, whether you got it right or not right, I think it's good practice for you to try to work on these things on your own. And if you didn't do it, then maybe you should, without looking at these solutions, try to redo it. So I'll put these solutions up as part of last week's notes. And then, because there's notes up there right now that only goes up to that example that, where we got stuck, I got stuck. And then, so I won't replace that, but I'll add on this page to that, to the notes online. Okay. So in terms of these undetermined coefficients, I want to do one more example with a higher order, higher than the second order, and then I want to switch to another approach. All right, so that's the plan for today. So let's do another example of undetermined coefficients. So the process that we're dealing with are undetermined coefficients, because you assign the A and the B and the C as these coefficients, and then you're going to try to solve for them. So I wanted to get to a higher order differential equation. Let's see. There's some higher order ones here. 21 through 26. Which ones do you guys want to do? Interested in? 23? So we got a third order differential equation. And then we have a right-hand side that has an x and a 4e to the x. So this would be a good time and maybe our opportunity to split this up to two different non-homogeneous differential equations, so that we can deal with two separate particular solutions that we're gonna attack at different times without having to try to do it all at once. All right. Oh, I need to do that. All right, so the first thing to do is to figure out our homogeneous set. So let's first consider y triple prime minus 3y prime double prime plus 3y prime minus y equals 0. And if you let y equal to e to the mx and do the factoring out the e to the mx, you'll get your characteristic equation again. M cubed minus 3m squared plus 3m minus 1 equals 0. So the tricky part here is to try to figure out what the solutions are for this cubic polynomial. And what we hope for is we hope to see if we can factor this. Or you can try to figure out by plugging in guesses. You can guess at your solution. Generally, you can just, or you can graph it and figure out the intersects, where they intercept. But if you were to do this kind of symbolically, you could take that -1 and say, oh, what if x is equal to 1 or -1 or m? So the one way to do this is to put your guess of a solution in there. Like, what happens if I put m is equal to 1? So m is equal to 1 would work, right? Yeah. Yeah. But we'll do it the fun way. If you notice that this is a 1, 3, 3, 1, and if you know Pascal's triangle, probably know that this is a binomial. You guys see that? No. Oh, there's all kinds of tangents we can go into. But let's take the current idea that I had. M equals to 1 is a solution, or let's call it a root. M is equal to 1 is a root, so m minus 1 is a factor. And if m minus 1 is a factor, you can do a long division problem here. M minus 1 divided by m cubed minus 3m squared plus 3m minus 1. Remember long division? Or you could do log or synthetic division, whatever. So I think to match this up, I need to multiply this by m squared. This is m cubed minus m squared, and then I'll get -2m squared minus or plus 3m, and then so I need to multiply this by -2m minus 2m squared plus 2m, and I get subtract, I get positive 1, m minus 1, and that's just 1. This would be 3 minus 2, what? Oh, yeah. So I think this is what we want. I want to subtract each of these things, right? So I get m minus 1, and this, so if I put the last one is going to be 1, so this is m minus 1, blue. So then that's complete, and so my factors are m minus 1 times m squared minus 2m plus 1. which factors to m minus 1 squared again. And so m minus 1 cubed. So this is equal to 0. So m is equal to 1 is your root of multiplicity 3. Right? So that means your fundamental solutions. Now this is a third order differential equation, so you will have 3 fundamental solutions. And based on your root, you get m is equal to e to the 1 times x is 1 solution. And since this is repeating, by the reduction of order, we can just tack on another x in there. Actually, we're going to do it twice. So without really doing it, without doing the reduction of order, we can just conclude that our 3 fundamental solutions are e to the x, x times e to the x, and x squared times e to the x. Okay? So that's the first part. Next, we have to find particular solutions. By the way, do you guys know what I meant by Pascal's triangle? Remember that triangle? So this is a little off to the side tangent. Remember that? Never seen it? So there's going to always be ones on the outside, and to get the terms in the inside, you add the 2 numbers above it. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. So these are coefficients for x minus y or x plus y raised to the nth power. If you were to FOIL that out, these would be the coefficients that would go along with that. So if n is equal to 2, if n is equal to 2, well, if n is equal to 0, then anything to the 0 power is just 1. If n is equal to 1, then it's just x plus 1, so the coefficients are 1 and 1. If n is equal to 2, this would be x1 times x squared plus 2 times xy plus 1 times y squared. And if you were to say x plus y to the 3rd power, so that's 1 times x squared, and then 3 times x squared y, and then 3 times xy squared, and then 1 times y to the 3rd. Anyways, you can mess around with that if you want. But those so I noticed that there's a 1, a 3, and a 1, and the signs alternate, so there should be a negative in between. Anyways, that was a little aside. Go back to step 2. So this is a case where we probably want to break it up to 2 different scenarios. We're going to consider y triple prime minus 3y double prime plus 3y prime minus y is equal to x. And then just deal with this to find a particular solution with the x in it. And fortunately, x is not linearly dependent with any of our fundamental solutions. So we can just take a guess of what our solution is going to be. So y sub p, and I'll put sub 1 here because we have 2 different particular solutions that we're dealing with, is equal to what? What? Ax plus b. It's a linear term. Well, Let's work, yeah. Oh, we're gonna do that separately. Yeah. So we're gonna take advantage of the superposition principle that says if we have things that we're adding on the right hand side of the original differential equation, we can just take it piece by piece, and so we'll have an easier time working things out. I might take a little bit longer, but not that much more. All right, especially if it's a polynomial, because after a couple of derivatives, we have zeros. Y sub p sub 1 prime is going to be a. Y sub p sub 1 double prime is 0. And so that's the same for y sub p sub 1 triple prime is 0. So we can just plug all that stuff into our differential equation. We have 0 minus 3 times 0 plus 3 times a minus y, which is ax plus b, is equal to x. So we'll match the coefficients of the terms, the x term and the constant term. We have minus ax plus 3a minus b is equal to 1 times x plus 0. So, and negative a is equal to 1. And then 3a minus b is equal to 0. And then 3a minus b is equal to 0, but a is equal to negative 1. So b equals negative 3. So we have one of our particular solutions. Y sub p sub 1 is going to equal to minus x minus 1 times x minus 3. So in the end, we'll put that as one of our solutions after we string up the x e to the x e to the x squared e to the x with the constants and stuff. Yeah. Oh, I just set them equal each other. Um, so if you have two polynomials that are equal to each other, you just look at the coefficients. So negative a is going to equal to 1. Maybe I should circle it. Negative a is equal to 1. And 3a minus b is equal to 0. So we set them equal. We have two equations and two unknowns, but we didn't do anything. We didn't have to do anything fancy for this. All right, that's one down. The other one should still be green, but maybe I'll. So the other one is to solve for y triple prime minus 3 y double prime plus 3 y prime minus y is equal to, and then that's a minus 4 e to the x. Now, your yp sub 2, the second particular solution, would normally be some constant times e to the x. But unfortunately, that matches with that. And if I multiply that by just an x, it'll match with this. And if I multiply that with another x, it'll match that. So we need to go x cubed. That's a bummer. Y sub p2 should actually be equal to c times x cubed e to the x. Because anything that's a linear combination of these will go to 0. And if we set that, if we put any of these things into the differential equation, it'll be 0 on the left-hand side and negative 4 e to the x on the right-hand side, which isn't going to work. So this is our guess, which means we need to take 3 derivatives. Oh, I don't like this problem anymore. We need to take 3 derivatives, and they all involve product rules, so let's be careful with that. Y sub p sub 2 prime is equal to what? What? What's a table method? So that's kind of like that's, I use a table for the, if you have to do integration by parts a bunch of times. Let's see if that so cx to the third e to the x. You just take derivatives, right? Wait, is this gonna work or no? So are you thinking about the table for integration by parts? Not for this. Okay. There must be a quicker way to do like the product rule a bunch of times. Yeah, well, from alpha will take care of that. All right, let's do it painfully. I mean carefully. Derivative of the first times the second plus the first times the derivative of the second. All right, first derivative, okay. Okay, now there's 2 of them. We have to do the product rule for each of them. Y sub p2 double prime. So derivative of the first, 6cx times the second plus the first, 3cx squared times the derivative of the second. All right. And then we have derivative of the first, okay, times the second plus the first times the derivative of the second. All right. So before we work this out, we want to put things together here just so we don't we make our next derivative a little bit easier, and it looks like we can combine these two. So let's rewrite that as might as well, huh? That's already there. We should have done that in the beginning. That's like for the first derivative already. Oh well, let's keep it on. E to the x plus 6cx squared e to the x plus cx cubed e to the x. So now third derivative. First one, derivative of the first, 6c times the second plus the first times derivative of the second. All right, so that's done. Now the next one, derivative of the first, that's 12cx times the second plus the first, 6cx squared derivative of the second. So that's done. And then finally, derivative of the first, 3cx squared times the second plus the first, cx cubed x. So a couple of things that we should be able to combine here. We got these two, and we got these two, and then the others kind of just are there. So yp2 triple prime is equal to 6c e to the x plus 6 and 12 is 18, cx e to the x, and then 9 cx squared e to the x, and then plus cx cubed e to the x. I'm glad there's no negative signs here. That would have confused things a lot more. All right. So we'll put that into our differential equation and then solve for everything. Actually, before we put it into a differential equation, let's just see if we can take Ali's advice and factor out a c, but we can also factor out an e to the x, right? Let's see if we can do that factoring business. So I'm going to squeeze it in here. We have factoring the c e to the x out. We get 3x squared plus x cubed, right? That's for the first derivative. The second derivative, if we can factor that out, put that over here. This is our second derivative right here. We can factor out a c e to the x again. What do we have left? We have a 6x plus 6x squared plus x cubed. Right? And then for the last one, we factor out a c e to the x. We get a 6 plus the 18x plus 9x squared plus x cubed. Okay? So I'm going to put all this together. Oh, boy. Probably not this particular problem. But it could be in the homework, right? It is in the homework. All right. So taking the CE to the X out, we just have these things in parentheses times whatever coefficients we're multiplying by. And the first one has a coefficient of 1. So I can just write 6 plus 18x plus 9x squared plus x cubed. Now the y double prime has a -3 on the outside, so I'll put a -3 in there. And the y double prime, after we take out a c e to the x, is going to be a 6x plus 6x squared plus x cubed. And then the y prime, after we take a c e to the x out, would be +3 times the thing here, 3x squared plus x cubed. And then after we take a c e to the x out, we just have an x cubed for that last one. Yeah, we hope that a bunch of things would cancel because the right-hand side doesn't have anything with an x in it. So just to make sure that they are going to cancel, let's take our canceling color red here. The x cubed and the x cubed and the -3x cubed and the +3x cubed all go away. Are we good with the x cubes? I mean, you can multiply the -3 and the +3 out, but if you do that, we'll see that these things will go away. And the x squareds, there's a 9 here. There's a -3 times 6, so that's a -18 plus 9. Let's see, double underline. And then a 9 positive. So we have a +9 minus 18 plus 9, so that goes away also. And then the x, there's an 18, there's a -18, and then that's all. That's gone. So everything's gone except for a 6c e to the x. 6c e to the x equals negative 4e to the x. So fortunately that worked out. You get rid of e to the x, divide by 6, and you get negative 2/3. Go. Oh, they still cancel. I canceled wrong the first time. See, 2 rights make a wrong. Or 2 wrong make a right. Yeah. Because the right-hand side of your differential equation is some number times e to the x. So you match up the e to the x, a constant times e to the x. Oh, because e to the x is linearly dependent with one of the fundamental solutions. And so we would normally multiply by x. We do that, we get another one. We do that, we get another one. So we have to do it 3 times. So that's it. We are done. So to finish off this part, y sub p sub 2 is equal to negative 2/3 e to the x cubed e to the x. Okay. So now we string it all together to get our final solution. C1 e to the x plus C2 x e to the x plus C3 x squared e to the x. So that's our solution for our homogeneous differential equation, our general solution. And now we put in our 2 particular solutions. And the first one was minus x minus 3. No, we don't put c's in front of the particular solutions because they have to actually satisfy the non-homogeneous. And then we put in our last one here, minus 2/3 x cubed e to the x. And if you had initial conditions, you should have 3 initial conditions. You solve for C1, C2, and C3. Okay. So maybe I'll give you a problem on the test where the solution, the general solution is here, and you just have to solve for the constants. I mean, after I give you a problem where you have to solve for the others. So it'll be 2 different problems. Yeah. Or I could just give you this one problem with an initial condition. All right. So we're going to skip over 4.5, the annihilator method. If you're an honors person, that could be one of the things that you can cover in detail. What? No, it's the same. It gives you the, they're not the same thing. It gives you the same results. In other words, the the undetermined coefficient methods would only work for these types of functions. And it turns out that the annihilator method would also only work for these types of functions. So it doesn't give you anything new. So in light of that, I'd just rather have you use this to solve for the problems on the test. So if you have a function that's not one of these, like a log function or a tangent function or another trig function that's not sine or cosine, then you cannot use this particular method. Because you know, the derivative of polynomials is still going to be polynomials. The derivative of exponentials is still going to be exponentials. The derivative of sine and cosine would be sine or cosine. That's why when you just have just a sine or just a cosine, you include both the sine and the cosine because their derivatives are there. But if you think about the derivative of a tangent, what's the derivative of tangent? Secant squared. So you jump to secant squared, and then derivative of secant squared is 2 secant and secant tangent. So there's a combination of secants and tangents that pop up there. And if you were to try to incorporate that into, you know, one of these formulas, that'll include a lot of different possibilities. The ln, the derivative of the ln is 1 over x. The derivative of that is what? Negative 1 over x squared. You keep taking derivatives, now you have something that, you know, 1 over x squared, 1 over x to the fourth, and all kinds of other things that's going to be too much to worry about and to handle. So it's not going to stay within the parameters of your function like a polynomial or exponential or sine or cosine do. So in that case, this won't work, and neither would the method in the next section that we're skipping. So we have to do something. For that, we'll use what's called the variation of parameters. So what is a variation of parameters? It's all this stuff over here. So I just copy everything? Might as well. So our progress or our progression is still going to be the same. We need to solve for the non-homogeneous differential equation first, and then we find a particular solution, and that's the key, is to find a particular solution. And by the way, you can use this for those functions that we already know how to solve for, like the e to the x and polynomials and stuff. You can use the idea of the variation of parameters for that as well. Except this is going to be a little bit more difficult to deal with, and it turns out that undetermined coefficients is easier, and so that's why that was introduced first. So what do we have? We go through the process of finding the solutions to the homogeneous differential equation, our fundamental solutions, y1 and y2 first. And the key here is to assume that our particular solution has some component of those homogeneous solutions as well. And so the process is to first find the complementary solutions. And given the two solutions that we have, the y1 and y2, we're going to find the Wronskian. And then we're going to rewrite the differential equation so that the highest order, in this case, the second derivative of the unknown function has a coefficient of 1, so that's like the standard form or normal form or whatever it's called. And then what we're going to do is we're going to solve for, or we're going to find a couple of determinants, w sub 1 and w sub 2. And the w sub 1 will have the same second column as your Wronskian, but the first column will change. And w sub 2 will have the same first column, but the second column will change. And then we're going to find a couple of functions, u sub 1 prime and u sub 2 prime. Does this look familiar? Like what? No. Look at the W1 over W and the W2 over W. And remember the matrix with a straight edge sign is the determinant, right? Does it look familiar? The discriminant? Yeah, closer. What? Cramer's rule. Remember I introduced Cramer's rule the other day? Just heard this is kind of like a linear algebra, and then after that it's just blah 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 blah. Did you hear something like this is not going to be on the test, so you just didn't pay attention anymore after that? Well, I actually threw in that Cramer's rule because these equations come from Cramer's rule. And if you look at the textbook and try to follow the proof, which we're not going to do in this class, I'm just going to give you formulas. But if you try to follow the proof, you'll see that they actually do use Cramer's rule, and this is where the W1 and W2 come from. They're like the determinant of your 2 by 2 matrix, except you're going to replace one of the columns with your right-hand side. And from here, you can try to gather what your right-hand side and your left-hand side are. So anyways, we're interested in finding two functions, u1 and u2, and you can solve for them by using these Wronskians. And your particular solution is actually, they're not technically a linear combination of y1 and y2 anymore, because u1 and u2 are not constants. When we talk about linear combinations, they're multiplied by constants. But in this case, they're actually multiplied by functions that we found. And the particular solution is going to be the first function, the y1 function that we found, matched up with the u function that we just found. All right. So we could try to do this method using a problem that we already know the solution to, or we can just dive in and just do another brand new one. What? Oh, 15 minutes, plenty of time. We'll take up about half a problem in 15 minutes. All right, let's oh, you know what? I'll just say, why don't you guys try to do one of these problems that we already did, like something like this, or maybe even easier, something like this. Do it with the undetermined coefficient. Okay. Yeah. Yeah. Why don't we do that? Sorry, Yasmin wanted to do a new problem, but let's do this. The first one, the one that we've been working on, is called the undetermined coefficients. This one is called the variation of parameters. It's no. But this one is necessary because it'll handle when the right-hand side's not a nice function like a polynomial, exponential, or sine, cosine. What? Yeah, it's more general, like be able to handle tangents and ln's and stuff. All right, let's give this a try just so we can get the process down, and then we'll do one with an actual problem. So just keep in mind what the components are that we need. So if we do this as a step-by-step process, the first step is always just finding the homogeneous solutions. So this is your step one. Then you do your Wronskians, and then you find your modified Wronskians, and then you set u1 and u2 primes, the derivatives, to equal to these things. And then if you have u1 prime is equal to a function, how would you get u? What? If I have u1 prime, how would I get u1? Take the integral. So you would integrate. I guess this is step 5. And then you would just tack each of those solutions with the fundamental solution that you already found. And then you would put it all together. So we could take a look at this as a 7-step process. And the other one had 3 steps, right? I mean, each step was a little long, but 3 steps. So this is clearly a little bit more involved. But like I keep saying, it's going to give us solutions to some non-homogeneous differential equations that we wouldn't be able to find using the other method. All right, so let's find the homogeneous solutions first. I think we already had this. Y double prime minus 10y prime plus 5 equals 0. Y1 and y2 were equal to e to the negative 2x e to the negative x. What? Oh, this one. E to the 5x, x e to the 5. Oh, we should have done the first one. That would have been easier. All right, so e to the 5x, x e to the 5x. So that's our first step. So the next step is to do the Wronskian. So we need to take the derivative. So w is going to be equal to e to the 5x. And somebody asked last time, is it important to figure out why did I put y1 equal to this and y2 equal to that? I said it didn't matter. But now, because we have to match up the y1s with the u1s, it's going to matter. It doesn't matter which one you choose, but as long as you're consistent, you remember what you called y1 and y2. So the derivatives also, oh, this one's another product rule. Plus the first, derivative of the second. And so you need to do the determinant, e to the 10x plus 5x e to the 10x minus 5x e to the 10x. And we get things that are going to cancel, so we just have e to the 10x. So that's my Wronskian. That's step 2. Step 3, we need to find the modified Wronskians. So W1 is going to be, so for W1, you replace the first column and leave the second column alone. What do you replace the first column with? You replace it with a 0 on top and then f of x in the bottom. So the 0 on top makes it nice because that's just going to disappear, make the other one disappear. And the f of x on the other side is 30x plus 3, right? or 30, yeah, 30x plus 3. And then we keep this the same. Actually, it doesn't matter what this is because it's going to be 0, right? So gone. And then we have 30x squared e to the 5x plus 3x e to the 5x. So I can't combine that, unfortunately. Well, we'll leave it like that. Oh, let's throw in the negative sign. Yeah, I took out the negative sign. Good catch. And then so my W2 is going to be e to the 5x, 5 e to the 5x, and 0, and then 30x plus 3. And so that would be 30x e to the 5x plus 3 e to the 5x. Okay, so far, so good. All right, now we need to take each of them and we're going to have that to equal to y1 prime after we divide it. So it's w1 divided by w, and this is going to be a 30x e to the 5x x squared plus 3x e to the 5x divided by, what was w? E to the 10x. Yeah, so that just cancel. Was it negative? What was negative? Oh, yeah, that negative sign that Luis brought up. So this is going to be minus 30x squared e to the minus 5x minus 3x e to the minus 5x. So we need to integrate that. So let's see. Uh-oh. My computer's starting to freak out. It's saying, it's too hard. Stop. Can't take all this math anymore. U1. So we need to integrate this. Let's see. Is there a quick way integrating this? This is where we do that splitting up. But there's two of them. Wait, before we do that, why don't we split this up, factor out an e to the negative 5x. So this would be minus 30x squared minus 3x times e to the minus 5x. So we can think about the integration by parts just happening one time. So integration by parts, I think we have the u and the v, but I guess I can't use u and v's because there's a u there. How would we do this? Minus 30x squared minus 3x and e to the minus 5x. So we take the derivative of one side and integrate the other, and this is the one that we take the derivative of, right? So minus 60x minus 3 minus 60, and then it'll eventually become 0. Integrate. So integrate, they become denominators. So minus 1/5 e to the minus 5x. This becomes a positive 1 over 25 e to the minus 5x. And we probably need to do it one more time. Negative 1 over 125 e to the minus 5x. And then we do positive, negative, and positive. So our u1 is going to equal to minus 30x squared minus 3x times 1/5 negative. So that's positive, and then negative minus 60x minus 3, and then 1 over 25 e to the minus 5x, and then positive negative 60 1 over 125 e to the minus 5x. So that's u1, and then you'll take that and you'll multiply that with y1. What was y1 again? Oh, just e to the negative 5x. And then do it all again for this u2. So u2 prime is going to be w2 divided by w, 30x e to the 5x plus 3 e to the 5x divided by e to the 10x. And then you would integrate that. So there's, that's going to be a couple of integration by parts. Now, if you look at our solution looks like there's a lot of e to the x, e to the x, e to the 5x. The answer that we got here looked like it was pretty clean, and then we have a couple of, we have this extra constant term, right? And so if we were to do this, what we're going to have is we're going to have a lot of extra terms that's going to contain e to the x and e to the x, e to the 5x. And then anything higher would probably just get canceled out. And so the only thing that's probably going to matter here are, oh, and then we're going to multiply this. Let's take this u1. So u1 times y1 is going to be this big mess over here. And what's y1 again? y1 was e to the 5x. So we have a bunch of e to the negative 5x's in there that will cancel out. And after we cancel those things out, you'll see that all we'll have left is a polynomial, right? And that's pretty much what's happening here. All that's left over here are polynomials. So that's what we should be expecting. All right? So you can go ahead and try to finish this. I'll work on this and finish this up on a separate, nah. Nah. Well, then do it without extra credit so you can learn. All right, so good luck with the rest of this stuff. When we come back, we'll dig deeper into some examples that don't have those things that we could have solved for earlier.